morning. It's a pleasure to have Anna Balibanu from Harvard University, and she will speak about partial compactification of the universal centralizer.
Thank you. Is it on? Yes. So I want to thank the organizers for the invitation to speak. It's really a great pleasure to be here. So I am a representation theorist, and representation theorists nowadays are very interested in symplectic and Poisson structures that show up naturally on algebraic varieties. So today I will try to describe one of these structures, and it will have a construction that is very representation theoretic. And for all the representation theoretic machinery, I will try to give concrete examples so that it doesn't seem too arbitrary. So throughout this talk, G will be a semi-simple connected algebraic group over the complex numbers. And I will require for G to have trivial center. So this is usually called being of adjoint type. So you can imagine that, for example, this group is PGLN. And then fractor G is its Lie algebra, which in this case is SLN. And then to every point in the Lie algebra, I associate a corresponding subgroup called the centralizer, which is the group of elements of G whose adjoint action fixes X. So when I write dot, I mean add. And because I chose this group to be of adjoint type, then these guys are connected. OK. So then inside this Lie algebra, we have a special class of elements that are called regular. And a regular element is one whose centralizer has minimal dimension. So the smallest dimension that a centralizer can have is equal to the rank of the group, or the Lie algebra, which in this talk we'll call L. So you can think of this as meaning that the adjoint orbit of X is maximal, or you can think of it as meaning that X is, that the orbit of X is a regular symplectic leaf when I identify G with its dual via the killing form. And then G is equipped with the Kosten-Kirillov Poisson structure. OK, let me give some examples to illustrate what these elements and what their centralizers are allowed to look like. So if I am in SLN, all my groups and my Lie algebras are over C, so I will suppress this notation. If I am in SLN, an element is regular if and only if, when I conjugate it into Jordan normal form, the Jordan blocks have distinct eigenvalues. So for example, a regular semi-simple element, which is one that is diagonalizable, is diagonalizable with distinct diagonal entries. And then its centralizer is conjugate to the subgroup of diagonal matrices. And this is a torus of rank n-1, which is the rank of SLN. So I should say this is a maximal torus. And this is true in in general, not just in this example, that if I pick a regular element that is semi-simple in the more general sense, then its centralizer is a maximal torus in the group. Okay, but in the semi-simple setting, we also have a kind of opposite extreme to semi-simple elements, which are nilpotent elements. So nilpotent elements in SLN are ones for which every eigenvalue is 0. They're just a sum of nilpotent Jordan blocks. But if I want the Jordan blocks to have distinct eigenvalues, then a regular nilpotent element is one that's conjugate to the maximal nilpotent Jordan block. And then if I compute the centralizer of the sky, I will get a subgroup of unipotent matrices, which will have ones on the diagonal, and then along the superdiagonals, they will have constant entries, and 0 here. So this is still an abelian subgroup of dimension n minus 1, but it's no longer a torus. It's a product of copies of C. And in general, I will write greg for the regular locus. And this is a dense subset of the Lie algebra. And if you want to see this concretely, you can think that any matrix can be approximated by diagonalizable matrices, and in fact, by diagonalizable matrices with distinct eigenvalues. Okay. So now, inside my regular locus, I will fix an SL2 triple. So this is a triple of regular elements. E and F are nilpotent, H is semi-simple, and together they generate a copy of SL2 inside the Lie algebra. And all of these triples are conjugate under the action of G, so it doesn't really matter which choice I make. And I'll use the same convention for annihilators in the Lie algebra, which are the Lie algebras of centralizers, using superscripts. And then we have a very famous theorem in representation theory of constant that says that if I take the affine space obtained by adding the regular nilpotent F to the annihilator of E, the following two things happen. First of all, it's contained in the regular locus, so all elements of this form are regular. And second of all, it intersects each regular G orbit exactly once and transversally. So you can think of the slice as a kind of parametrization of regular orbits, or of regular conjugacy classes. And probably this theorem is very suggestive to this audience in particular, because what this actually is, so remark, what this actually is a Poisson transversal to this Poisson structure. So this is a Poisson transversal in G when I identify it with G star. This seems to be known, but I have never found a reference for it. So if anyone knows a reference for this fact, I would be very happy to also know it. Okay, so if you want like a very concrete picture of the space, you can think of it in the case of SL3, where the slice looks like 3 by 3 matrices that have zeros on the diagonal, constant superdiagonals, and ones on the first subdiagonal. And this is A and B, are allowed to be complex numbers. And what this theorem says is that every matrix in SL3 whose Jordan blocks have distinct eigenvalues is conjugate to a unique matrix of this form. I welcome questions about this entire setup. And in the meantime, I'll erase the sugar loaf. Okay. So now we can define the main character of this talk, which is something called the universal centralizer. And this is the algebraic variety that consists of pairs, G in the group and X in this affine slice, with the property that G centralizes X. So you can think of this, it has a natural projection to the slice, and you can think of this as the family of centralizers of regular elements parametrized by their conjugacy classes. And for reference in the future, so what is the dimension of the sky? Well, the base is parametrized by one regular centralizer, which has dimension the rank. And the fibers are also regular centralizers, so they also have dimension equal to the rank. So this is an even dimensional algebraic variety of dimension 2L. And the remarkable thing is that this variety has it comes equipped with a natural symplectic structure. And traditionally, the symplectic structure is obtained through a procedure that we call constant Whittaker reduction. So first I will explain the procedure, and then I will explain this strange name. So throughout, I'm still using my fixed regular SL2 triple. And in this triple, I have a regular nilpotent E. And this regular nilpotent E is contained in a unique Borel subalgebra, which I'll call fractor B. A Borel subalgebra is a maximal solvable subalgebra, and in SLN, it means exactly that it's a subalgebra conjugate to the upper triangular matrices. So the statement is saying that this regular nilpotent lives inside here. Okay. And now I can associate a bunch of things to this. So there's a Borel subgroup whose Lie algebra is this fractor B. This is a subgroup that is maximal with the properties that it's connected and solvable. And inside this Lie algebra, I have its nil radical, so this is the collection of all nilpotent elements. In this example, these are the strictly upper triangular matrices in SLN. And this nil radical also integrates to a subgroup of unipotent matrices, which in PGLN look exactly like you would expect. Yes? what a coincidence that you should make this observation. Yes, so I will say this. I will say this. It's a Poisson transversal inside the cotangent bundle. But I am trying to give a construction that is both historical and generalizable. Yeah, so then what happens? Well, on the cotangent bundle of G, we have a two-sided action of the group. And in particular, a two-sided action of this unipotent subgroup. And this action comes equipped with a moment map, which I'll call mu n, to the dual of the subalgebra. And we can understand this moment map very explicitly because we can factor it through the moment map of the action of G cross G. So what this means is that I trivialize the cotangent bundle with respect to the left action, and I identify once again G with G star. And then I have here a moment map for G cross G, which takes a pair Gx to G applied to x comma x. So as Rui already observed, the fiber above a diagonal element is isomorphic to the centralizer corresponding to that element. And the image of this map is the subvariety of conjugate pairs in G cross G. And then I can make the following identification. So n star through the killing form becomes identified with G mod B, and then this diagram is completed by a projection. Okay, so now I want to do a Hamiltonian reduction with respect to the action of this unipotent subgroup. So I will choose a fixed point in the image of this moment map, and this F is exactly the F that I fixed over here. And to believe that it is really an n cross n fixed point, you have to imagine F as being this kind of subdiagonal nilpotent. And then when you act on it by strictly upper triangular matrices, you move upwards. But because you are quotienting by the Borel, you are killing this upwards movement. So what happens, this point is fixed by n cross n, and the action on the fiber is free. And when you take the quotient, you get exactly this variety Z that we called the universal centralizer. So Z is a smooth symplectic variety. And the remark that was spoiled by Rui is that if you know that, that this affine space gives you a Poisson transversal in the Lie algebra, then you can upgrade it to a Poisson transversal in G cross G. And then when you take its pre-image under this moment map, you will get something isomorphic to Z. So in many cases, actually, well, let me say first, the reason why this construction is called constant Whittaker reduction is because it appears, at least implicitly in various papers of constant, and we call Whittaker reduction Hamiltonian reduction with respect to the action of a unipotent group at some kind of appropriate regular point. And I think this was introduced by Whittaker and has some motivations in physics. And in many examples that I know of, this kind of Whittaker reduction can also be realized like this, by taking a preimage of a Poisson transversal, but I think no one has ever studied this, so there are no general statements. Yes? Well, yes, because this is, I mean, projection to the slice, you can imagine that it comes from restriction of this moment map, which is Poisson. Yeah, so it's actually it's a bit stronger than a groupoid. It's a group scheme. So somehow both maps are the same, and this is, you can think of this as a scheme living over this affine base, and this is often how people consider these things in algebraic geometry. And then the fibers are groups, and you can define what it means for it to act on other schemes that live over the space. In fact, we will construct such a scheme. Any more questions? Okay. So the goal. Remember that we think of this as a family over this affine slice where the fibers are centralizers. And I want to give a partial compactification of this family in this fiber-wise direction. So I want to compactify the centralizer fibers in such a way that I get a smooth variety at the end. And that I can extend the symplectic structure to some Poisson structure on the total space of the compactification. Okay. So the nice fact is that because we're working with a semi-simple algebraic group with no center, there's a very natural place to look for compactifications of subgroups, because these adjoint type semi-simple algebraic groups have a canonical compactification that is called the wonderful compactification. So this was introduced in the 80s by De Concini and Procesi in a slightly more general setting of symmetric spaces. And since then, these wonderful varieties have been studied a lot, and it's been shown that, in fact, you can build compactifications like this for sort of special classes of spherical varieties as well. So I will give a sort of quick outline of how this thing is constructed. We'll need G tilde, which is the simply connected cover. Of G. So if G was PGLN, then G tilde would be SLN. And then I will fix a regular irreducible representation of G tilde. So to be regular, this also appeared in Anton's talk as a kind of generic condition. If you imagine that irreducible representations of G tilde are parametrized by by points in the dominant Weyl chamber, then this means that your highest weight does not lie on any walls. So if we are in the case of SL2, the irreducible representations are parametrized by non-negative integers, and you are regular if you are not zero. And if we are in SL3, they are parametrized by this lattice in the plane of dimension 2. And the dominant chamber is this cone over here, and you are regular if you are in the interior of the cone. Okay, so I fix this data, and then I get the following diagram. So the representation map takes G tilde into endomorphisms of V, and in fact into non-zero ones. And then on the left, I can quotient by the center, and I will get G. And on the right, I can quotient by scalars, and I will get this projectivized endomorphism space. And because the group I chose had no center, and because the representation I chose was regular, this representation map descends to an embedding of G into this projective space. So, definition, the wonderful compactification of G is just the closure of the image of this embedding. So I'll say some properties of this variety, and then I will give an example in small rank. So many remarkable properties. The first is that this construction is independent of the choice of regular representation. So all regular representations will produce the same compactification. And the second is that what you get is actually a smooth projective variety. So taking this closure doesn't give you any singularities. And then, inside G bar, we have an open dense copy of G. And on G, we have a two-sided action of the group by left multiplication and by right multiplication, and this extends to this compactification. So this gets the structure of a G cross G variety. And then I can look at the boundary. The boundary is codimension 1, so it's a divisor. And it has as many irreducible components as the rank of the group. And these irreducible components are smooth, and they intersect in normal crossings. So this is smooth normal crossing divisor. And then I can look at the action, a two-sided action of the group on this boundary. And this is an action with finitely many orbits. And these orbits are parametrized by subsets of the integers from 1 to the rank, in the sense that if I take the closure of the orbit indexed by the subset I, this is the corresponding partial intersection of divisor components. So in particular, the orbit closures, the closures of the G cross G orbits on G bar are smooth. Okay. So let me say just a tiny bit about the structure of these orbits, because it is very compelling and will motivate why, when people discovered this compactification, they called it wonderful, even though it's not, strictly speaking, so essential to what we're doing. So if I have such a subset of integers, I can think of it as a subset of simple roots. And then I have two associated parabolic subgroups. You can think of them as an upper triangular parabolic and a lower triangular parabolic. So parabolics are just, in SLN, they are matrices which are block upper triangular. Okay, and then I have their intersection, which is a Levy subgroup. And this guy is reductive. And then there is the following fact. So with all of this data, if I analyze the orbit indexed by this subset I will get a fibration over this product of partial flag varieties. Like I said, this is not totally essential to the talk, so I won't give very detailed examples of how this happens. And the fiber of this fibration is the quotient of this Levy by its center. So now that I've taken the quotient by the center, my reductive group has become a semi-simple group. And in fact, it has become a semi-simple group of adjoint type. And now I can ask, what happens when I take the closure of this orbit? And the answer is that it still fibers over this product of partial flag varieties, but now the fiber is the wonderful compactification of this smaller semi-simple group. So this is very beautiful boundary structure. And in particular, there's a unique, I should say this separately, there's a unique closed orbit of minimal dimension, which is the intersection of all the components of the divisor. And from this description, you can see that this will correspond to the two parabolics being opposite Borels, and to this fiber being trivial. So this unique closed orbit will be a product of two full flag varieties. So this is something called the flag variety of the group G. And in the case of SLN, it is actually the projective variety that parametrizes complete flags in n-dimensional space. Okay, so example of how this construction goes through for PGL2. So for PGL2, G tilde is SL2. And for SL2, I can pick any representation indexed by a positive integer. So of course, I pick the smallest one. And this is called the standard representation, which is exactly the one we know best, where SL2 just acts by matrices. And then this embedding chi that I obtained over here is just the embedding that takes PGL2 into the projectivized space of 2 by 2 matrices. And its image consists, of course, of matrices with non-zero determinant. So then you can see that where do I want? You can see that the closure of this image is the entire space, which is a three-dimensional projective space. And inside this closure is living the boundary, which consists of singular matrices, so matrices with determinant 0. This is a single G cross G orbit, because all 2 by 2 matrices of rank 1 can be translated one to the other by left and right multiplication. And in fact, via the Segre embedding, this is a product of 2 copies of P1. So now if you've seen this before, you know that P1 is exactly the flag variety of SL2. So this is consistent with this orbit structure. Okay. And now, to not be deceptive, I will also give a non-example to show that this PGL2 case doesn't generalize. So if G is PGLN, for n greater than or equal to 3, G tilde is SLN, the standard representation now is no longer regular, because now the standard representation is the one of the generators of this dominant cone. So it lives over here on the boundary. So standard rep not regular. And the wonderful compactification of G is not just an n squared minus 1 projective space, so it's something more complicated. So this is still a compactification. It just doesn't have the wonderful structure. And you can see this immediately if you think that the boundary here is cut out by the vanishing of the determinant. And this is an irreducible polynomial, but it gets singularities where the rank of your matrices drops. So this is no longer a smooth boundary divisor. Okay. So now I make the following definition. I'll write Z bar for the variety of pairs, A in the wonderful compactification, and X in the affine slice that I defined earlier, with the property that A is in the closure of the centralizer of X. And the theorem is that this variety is smooth, that its divisor, its boundary divisor, when I remove the copy of the universal centralizer sitting inside it, is a smooth normal crossing divisor. And that the symplectic structure on Z extends to a log symplectic structure on Z bar. When do I stop? Okay. Okay, so let me make some remarks about about what this variety looks like. Again, we should think of it as living above this affine slice, and now is a family of compactified centralizers. So now it's equipped with an action of Z as a group scheme. The action is just along the fibers. And I'll say just a couple of words about what the fibers look like, because this was the kind of motivation for constructing this variety in the first place. So remember that this base is parametrizing all conjugacy classes. So in particular, the conjugacy classes, all regular conjugacy classes. So these are varying from being semi-simple to being nilpotent. And maybe we don't need a. So if I take a regular semi-simple term, then its centralizer is a maximal torus. And so the fiber above this regular semi-simple term, which I'll call T bar, is a projective toric variety. And in fact, it's smooth. And if you remember that toric varieties are classified by their fans, then the fan corresponding to this one is exactly the fan of Weil chambers. So this is this guy also shows up in many other settings in representation theory, and maybe this is not surprising because it's a natural way to compactify the maximal torus of a semi-simple group. Okay, so the generic fiber is smooth, and we know exactly what it looks like. But then if I take a non-semi-simple element, then these centralizer closures get singularities. And in fact, they get singularities even in codimension 1. So these things are kind of interesting in their own right. These fibers are a type of algebraic variety called a Hessenberg variety, but often their geometry is difficult to study because of these singularities, which are in low codimension. So one way that this family is useful is that it kind of parametrizes a degeneration from a toric variety that we understand very well and that is very symmetric to a singular variety that is maybe significantly more complicated. Okay. So now I will say in the last few minutes how the construction of this Z bar goes. And the idea is that we want to play the same kind of game with Whittaker reduction that we did in the case of the universal centralizer, except we want to replace the cotangent bundle of G by something bigger. And the natural thing to replace it with is the logarithmic cotangent bundle of G bar. So this is the bundle whose sections are logarithmic differential forms with poles along this boundary divisor. And when I restrict it to the copy of G sitting inside G bar, then I recover the ordinary cotangent bundle of G. And this log cotangent bundle comes equipped with a canonical log symplectic structure and with a two-sided action of the group G that is Hamiltonian and that gives you a moment map. So I want to describe very quickly how to understand what this moment map actually is. And for this, I will give an explanation that is very special to the case of wonderful varieties of this log cotangent bundle. So we can see this guy as living inside the trivial G cross G bundle on the wonderful compactification as a subbundle. And I won't prove this. I will give a reference, which is Briand, but it actually follows from some more general results on wonderful varieties in Briand, so this actual statement you won't find there. So this means that its fibers can be identified with subspaces, hopefully subalgebras of G cross G. And this identification is very explicit. So if I take a point in G bar, and I take its orbit, which I'll call O, then I have an action of the stabilizer of this point A in G cross G on the normal space to O at A. And this action has a kernel. And I'll write G cross G lower parentheses A for the Lie algebra of the kernel of this action. And this Lie algebra always has the same dimension as G. You can prove this, and it follows from the boundary structure of the wonderful compactification that this is the case. And this guy is exactly the fiber of the log cotangent bundle under this embedding. Okay, so very quickly we can immediately see what some of these fibers look like if A is the identity in the group, and then the stabilizer is just the diagonal subgroup inside G cross G. And well, when this is the case, this orbit is the open dense orbit, so this normal space is trivial. So the special Lie algebra is the entire diagonal subalgebra in Lie algebra cross Lie algebra, I should say 1. And then because our picture is G equivariant, if I take some other element in the group and look at this fiber, it will just be a translation of this fiber. So it will be pairs of points of the form gx comma x. So already this is kind of recalling what our moment map looked like, and this is not a coincidence. So remark, there's an alternative way to construct G bar. Where I take the group G and I embed it into the Grassmannian of dim G-dimensional subspaces of G cross G. And I do this embedding by taking a group element and applying it to the diagonal subalgebra. And then G bar, the wonderful compactification, is isomorphic to the closure of the image of this embedding. And then this log cotangent bundle just becomes, I take the tautological bundle of the Grassmannian and I restrict it to G bar living inside the Grassmannian. this is also not, what I said about the tautological bundle is also not obvious, so somehow all of this is very special to the wonderful compactification or to slight variations of this. Okay. So now we're in good shape. So now I said that we want to do the same kind of Whittaker reduction that we did in the group case. So again, we have n cross n that is acting on this log cotangent bundle with moment map to n star cross n star. And again, this moment map is going to factor through the moment map for G cross G. But now I can say explicitly what this moment map is, because when I think of this log cotangent bundle as a sub-bundle here, moment map just becomes projection onto the fibers. So this is mu bar. And what mu bar looks like, or how it extends, this is if you restrict this to the copy of the cotangent bundle of G living in here, then you get the old moment map that we had at the beginning. And what you can show is that if X is a regular element, then the fiber of mu bar over the corresponding diagonal point is exactly isomorphic to the closure of the centralizer of X in the wonderful compactification. So this is not obvious because you've added some boundary. These fibers potentially could pick up new irreducible components of smaller dimension, all kinds of things like this. And the image of mu bar, if you remember, the image of mu was just conjugate pairs in G cross G. And now this is like a proper map. So what I've done is I've just taken the closure of the image, and I will get something that I will denote like this. I mean pairs that have the same image in the adjoint quotient. You can think of this as pairs that are not in the same orbit, but in the same orbit closure. And now if I do the same reduction, I will get my compactified universal centralizer Z bar as, here's F, and here's mu bar n as a quotient of this fiber by the n cross n action. And then it will be smooth, and it will be log symplectic. And if you kind of restrict this story back to G, you will get Z, the universal centralizer, living inside it as the open dense symplectic leaf. And another remark is that in this case, too, you can obtain, maybe I won't write it for time, you can obtain Z bar as the preimage under mu bar of some Poisson transversal. And this is about equally difficult. I mean, the tricky parts of this proof are mostly computing the fibers of this map, and you have to do that in either case. Okay, so I'm done.